Mhm, mhm, mhm. Okay, hello everyone in a new video. So we have reached part 4 of chapter 4, which is the chapter of resistors for grade 10 students. And eventually now we have reached section 7. And the title of this section is Relation between resistance and resistivity. Now we know that electric wires are responsible in an electric circuit for conducting electricity or conducting current. But till this moment, we didn't discuss the properties of these wires. So here let me consider only one types of wire that are cylindrical in shape. So if we zoom into the wire, we can notice that it is cylindrical in shape. So here by this is a circle. And this represents a cylindrical wire. So which is basically the connecting wires that we have used in different electric circuits. Okay, and now let me say the resistance can be defined in terms of the resistivity and the formula here that I will write is given by the following. So the resistance which is given by R, this is nothing but the resistance and it is related and it relates the voltage and the current for a pure resistor and it's given by U is equal to R multiplied by I. Now let me here say that the length of this wire is L. Then we have rho multiplied by L divided by S. So here this represents a circle of area S. So now let me define what does each quantity represent, where R is the resistance of the wire, and its SI unit is given by ohms, which stands for ohms. Rho is the resistivity of the material, upon which the wire is made up of, and it's given by ohm multiplied by meter, which is ohms meters. This is a derived unit. Now as for L is the length of the wire, and S is the area. This is known as the cross-sectional area. Now, it's difficult to observe this area by the naked eye, but suppose here that you have a wire like this, and if you cut this wire, then what you will observe here is a circle. So we are measuring the area of the circle. So, and its SI unit is given by meter square, which is given by meters square. And here, if the area is circular, then we know that the area of the circle is given by pi r square, in which r is the radius. So here we can represent r on the figure. So I have used a small r because I'm using capital R for the diameter, for the resistance. So this will be the radius r. Okay, so the same, so here also we have the area S, and this will be the radius r. Okay. Now here also let me say the following, that in order to convert, okay, so the conversion of the units regarding area I will discuss during the exercise. Now let me discuss a bit the resistivity and drag the following table that I have prepared. And let me write the following note. Previously, we have assumed that all wires are of negligible resistance, similar to the ammeter. Then the voltage across the wire is given by 0. But actually they are not negligible. So we can say that actually, or in reality, the resistance of the wires are not zero, which means they are negligible, but they are not zero. And as you can notice here, we have the value of the resistivity of several materials. And notice that they are multiplied by 10 to the power minus 8. So they are of order of magnitude 0.7 zeros multiplied by 1. 7 zeros, and we have 1. So this is the resistivity row. So when we calculate R using rho, so the value of R will be very small. For this reason, the resistance of the wire is not zero, but it is negligible. So if I'm using the formula that it's given by R is equal to rho L divided by S, and we replace rho, so here we have the resistivity rho of several materials. We have for copper, aluminium, graphite, silicon, and quartz. Notice that these have very high resistivity because they don't conduct electricity. So here the resistivity is very low, which means that they conduct electricity easily, because we know that as the resistance decreases, the current will increase. So usually in this case, we use copper because it's commercially cheap and it conducts electricity in a very good way. So the resistivity of the copper is excellent and it is cheap at the same time in order to consider considered in electric circuits. Okay, so although previously we have considered the voltage of the wire is zero, which means of negligible resistance, but in reality we can calculate the resistivity. So the resistivity depends on the material itself. We have the following resistivity for each of these materials. And what does resistivity reflects? Let me write here. Reflects the ability to conduct current. Okay. Now let's solve the following exercise, which is exercise number 8. They are telling us in the given circuit diagram we have R1, R2, 3, 4, 5, and 6. We have the value of I1, the value of I2, the value of I4. Now number 1. As I have mentioned previously, the trick in solving such type of exercises, although they seem to be complicated, but they are straightforward whenever we represent different electric circuits, whenever we are calculating equivalent resistance, and to represent the traverse current and the applied voltage. Okay, so number 1, they are telling me indicate the direction of current in each branch. So this is a simple electric circuit. Here let's suppose that the switch is closed. Okay, they didn't mention anything about the switch, so let's close the switch. Now in number 1, indicate the direction of current in each branch. So we know that the direction will circulate in the circuit from the positive pole to the negative pole. So here it will be like this. So this is the main current. At this point it will split like this, go back to the negative pole. So now going from here, it will be like this here, like this, going back to the negative pole. Now reaching this point, okay, part of the current will be directed like this and the other part will be directed like this, because this is simply a simple circuit and the positive pole will deliver the current to all other branches like this. Okay, so no way here the current will be like this, for example, because this is the main current and it's splitting like this in all branches. So now after we have indicated the direction of the current, let me place the values here. So this is 1.5 amperes, the value of I1. Now the value of I2 is given by 1 ampere. The value of I4, which is in this branch, is given by 0.6 amperes. So done. Now as for number 2, they are telling me calculate the value of I3. So where is I3? This is I3. So notice that here the main current so the current here I1 splits into two currents, I2 and I3. So let me say apply law of addition of currents at node A. So we have summation of current in is equal to summation of current out. Now the currents entering the node are simply I1, which is equal to I2 plus I3, the currents leaving the node A. And in this case we are interested in determining I3. So I2 and I3, they leave the node. So what's the type of this equation? This is a linear equation and one unknown. The value of I1 is 1.5. The value of I2 is 1 plus I3. So I3 is equal to 1.5 minus 1, which is equal to 0.5 amperes. So I3 is equal to 0.5 amperes. And the moment we calculate a current, let's place it on the circuit. Now in number 3, we need to calculate the value of the equivalent resistance of R1, R2, and R3. So this is the first part of the question. So we need to calculate the equivalent resistance of this grouping. So notice that simply we can start with R2 and R3 because they are in series. Then both of them are in parallel with R1. So R2 and R3 are in series. Then R23 is equal to R2 plus R3. The value of R2 is given by 10 and the value of R3 is given by 14, which is equal to 24 ohms. Now, although we can calculate them with R1, but it's more convenient now to redraw a circuit again, although the drawing of the circuit will be difficult for me. So now what I will do is the following. Okay, let me draw it again. No, wait. Let me do the following. So this is the second circuit that I have obtained. Now, because it's difficult for me on the PC to draw the circuit with the precision, but using a pen and a paper it will be much easier. So now let me complete the circuit and let me here say that here we have R2 3. We have the value of R2 3. Usually resistance is not labeled on the circuit, and here the value of the current that we have is given by the current I3, the current I3, which is given by 0.5 amperes. Now notice we need to calculate the equivalent resistance between R23 and R1, so they are in parallel. So 1 over R123 is equal to 1 over R1 plus 1 over R23. The value of R1 is given by 12, and this is 24. Now here you need to consider we are adding two fractions, so you need to consider the common denominator and the simplest form of a fraction. Plugging it on the calculator, then it's given by 1 over 8. Then in this case R123 1 over 8. Now crisscross, which means that R123 is equal to 8 ohms. Now let me represent a new circuit which is more simpler. and we have the value of R123, and notice that here in this case R123 is being traversed by the current I1, which is 1.5 amperes. Okay. Now in the same part they are telling me deduce the value of UPN. So whenever we apply equivalent resistance, it means that we need to apply Ohm's law to find the voltage. So now we need to determine the voltage UPN, or usually, okay, whenever we calculate equivalent resistance, we need to apply Ohm's law. Ohm's law can either give us the voltage if we know the current, or the current if we know the voltage. In this case, we know the current. So we can determine the voltage UPN by simply applying Ohm's law to R123. So we need to deduce the value of UPN. Then apply. So this is the initial circuit. This is the second circuit, and this is the third circuit. So apply. We are still in number 3. So let me write it here. Apply Ohm's law to R123, and here we are following a trick, something conventional for us, that whenever we say apply Ohm's law once in the exercise, we will not say it again. The same for the law of addition of currents, and the same for the law of addition of voltages. Then now U is equal to R multiplied by I, and we are interested in determining the value of U. No need to construct a triangle or anything. Sorry, not constructing a triangle. So R123 multiplied by I1. So we have 8 multiplied by 1.5, and plugging this on the calculator, I think this is 12. So 8 times 1.5, which is equal to 12, everything expressed in the SI, so this is 12 volts, and we are talking about the voltage UPN measured from the positive pole to the negative pole. So also the trick is to write the voltage here, voltages here. Here UPN is equal to 12 volts, and UPN is equal to 12 volts. UPN is equal to 12 volts. Now number 4, calculate the value of R prime, the equivalent resistance of R4 and R6. So notice that R4 and R6 are in series because they have only one terminal in common at the point C. Now, and also I want to say something. If you look at the shape of R4 and R6, so R4 is like this, and this is R6. Series and parallel, okay, we name them series and parallel. So these are in series. In series means beside each other, and in parallel above each other, like as if we are talking about parallel lines. But this, okay, this is to make stuff simpler, but it's not the correct terminology to refer to the geometrical shape of the resistors. They are in series if they have only one terminal in common. So now, for example, if you want to connect them in parallel, you can simply connect them like this. Take a wire from here, take a wire from here. Then they are in parallel because they have two terminals in common. This is the first terminal and this is the first terminal. So one should always keep in mind that series and parallel, they reflect the geometrical figure, but this is not the true story. The true story is that whenever they have only one terminal in common, they are in series. Whenever they have two terminals in common, they are in parallel. In this case, R4 and R6 are in series. So their equivalent resistance is denoted by R prime. We use the same notation, which is equal to R4 plus R6, which is equal to 13 plus 7, which is equal to 20 ohms. And we have determined an equivalent resistance. We need to represent it again on the circuit because this will make the task easier for us later. Now here we have, okay, we will not represent them on this circuit, however on the final circuit that we have determined, which is this one, which is more convenient. So now let me make another copy of this. Okay. sorry, this is not what I wanted. Okay, this will be more difficult. Let me say the following. Okay. So here, this is circuit number 4. Okay, so now it's easier for me to draw it. Now these two should be eliminated like this, and they should be replaced by a single resistor, which is like this. This is R prime. But notice now we can draw the circuit in more simpler way, because R prime and R5, they are in parallel. They have two terminals in common. So instead of representing this circuit, let me represent it in the following way. So here we have the battery. So let me write here that we have R123 is equal to 8 ohms, and R23 is given by 24 ohms. Then the next circuit that we are interested in is the following. We have resistor R prime. We have another resistor R5. They are connected to the battery, so we don't care about the switch now, it's a connecting wire. And here we have the resistor R23, R123, which is 8 ohms. This is 12 volts UPN. This is the point P, this is the point N. Okay, the point C will disappear. We don't have any points. Sorry. Okay, this is A and this is B. This is the current I1 is equal to 1.5 amperes. Here the current traversing R prime, which is the equivalent between R4 and R6, is I5. Okay, and here we have the current traversing R5. So the current I4 here the current I4 is the one traversing R4 and not R5. So I4, this is I4, which is equal to the current traversing the resistor R4, which is given by 0.6. So here this current is for the one traversing the resistor R4. So this is given by how much? 0.6 amperes. What else do we have? Okay, we don't care about the current I3 and I2 because simply it's replaced by I1. So this is it. And here we have the current I5. So how come I5 is represented here in R6? So let's see, let's suppose that now we will check if our calculation is correct or wrong. Let's suppose that I5 is the current traversing the resistor R5. Okay, now they are asking us to verify that I5 is equal to 0.6 amperes. Here we cannot use the law of addition of currents because we don't know this current like this. We don't know the value of this current because we don't know the value of the current in the main branch. So I5 can be simply determined by applying Ohm's law to R5 because we know the value of R5, and the value of R5 is given by 20. So let me say apply Ohm's law to R5. So we have agreed that we will not say Ohm's law anymore. Then U is equal to Ri. We are interested in determining the value of I. So I is equal to U divided by R, which is equal to the voltage of the battery because they are in parallel 12, divided by the value of R, which is given by how much R5? 20. Now plugging this on the calculator, this is eventually equal to 0.6 amperes. So indeed, my guess was correct, that here each current, this is I5 for the voltage UPN across the resistor R5. So here the currents are, so this is not I5, this is I6, and I5 must be here, okay? So each resistor is being traversed by the respective current, which is I5. So let me correct them, it's okay. This is 6, this is I4, and this is I5 here, okay? So similarly for the other circuits. So here we have I4 and I5. Now they are telling me calculate the value of the main current I. We are in number 6. So now we need to say apply law of addition of currents at the point P. Here let me say, because we need to mention at point P, or without mentioning since we mentioned it. So summation of I in is equal to summation of I out. Here we are talking about the point P. Now notice that if you consider this point to be, for example, the point C, now this is the in current and this is the leaving, so they must be equal. So this current here is actually nothing but I4 plus I5, okay? And here the current I. So the current that is entering the node at the point P is given by I, which is the main current, and the currents that are leaving, this one is leaving like this, which is I1, and also leaving this branch, this current is equal to these two, and they are given by I5 plus I4. And we are interested in determining the main current, which is I, traversing the battery. Now the value of I1 is given by 1.5, I5 is given by 0.6, and I4 is given by 0.6. Now let me check the value of the resistances. What is the value of R prime? R prime is 20, and what about R5? For this reason, since they are of equal resistances, the current will split equally. Okay, so in this case, 1.2 plus 1.5, this is equal to 2.7 amperes. So I is equal to 2.7 amperes. Now after we have determined everything, we can refer back to the initial circuit, and here we can safely say that the main current in the circuit is given by 2.7 amperes, and the value of I5 is given by 0.6 amperes, and these currents are equal to 0.6 amperes, and because they are series, they have the same current, okay? So now no need for these circuits anymore, because we have determined everything in the circuit. We have determined the currents, and we know the resistance. We can determine the voltages, for example. Now in number 7, finally they are telling me calculate the value of the equivalent resistance of the circuit. So we will refer to the final circuit we have done. So this is 4. Now notice that here we have 3 resistors, R123, R5 and R prime. All of them are in parallel, because you can consider that this resistor is connected like this, So let me say here the value of R5 is 20 ohms and R prime is 20 ohms. Okay. So now in number 7, R123, R5 and R prime are in parallel. Then we have 1 over R equivalent equal to 1 over R123 plus 1 over R5 plus 1 over R prime, which is equal to R123 is 1 over 8. Sorry, R123 is 8, which means 1 over 8 plus 1 over 20 plus 1 over 20. Now plugging these three fractions on the calculator, we have that it's given by 9 over 40. So 1 over R equivalent is equal to 9 over 40, which means that R equivalent, if you consider the crisscross, is equal to 40 divided by 9, which is almost equal to 4.44 ohms. So simply the circuit can be now simplified into the following. We have a generator, we have a resistor, R equivalent is equal to 44 ohms. Now the current that we have calculated is given by 2.7 amperes and the voltage is given by 12. And actually, in order to verify the following results, since we have calculated them in an independent way, let's try to multiply 2.7 by 4.4 4.44 ohms. So as a double check, 4.44 multiplied by 2.7 must give us 12. That's a check, because this is Ohm's law. And it's indeed 11.98, which is rounded to the nearest degree, which is 12. Okay, so all our calculation is correct. So now we can move on to part 2. They are telling us in part 2 that the resistance R1 is made up of an iron. Now, in the previous table that I have presented, we don't have the material, which is iron. Okay, however, here they gave us the resistivity of iron. So we are in part 2 of this exercise. The length L is equal to 20 meters. The material we are using is iron, which is a conductor of electricity. And the resistivity row, they call that, sometimes we use this symbol in mechanics for density, but here we are using it for resistivity, and it's given in the SI to be 10 to the power minus 7 ohms meter. Now in number 1, they are telling me to calculate the diameter. We know that the diameter is related to the area, related to the surface, related to the radius, related to the surface area. So if we are able to calculate the surface area, then we will deduce the radius and multiply it by 2 to calculate the diameter. All of these quantities are related to each other by the formula R is equal to rho L multiplied by S. And we are interested in determining the area, because if we calculate the area, we can determine the radius. If we determine the radius, we can deduce the diameter. So now we need to rearrange the following formula. Here this is divide, so it comes up, it will be multiply, and R comes down. So if you crisscross, putting S on one side and R on the other side, so S is equal to rho L divided by R. And here we are talking about the resistor R1. The value of resistivity of iron is 10 to the power minus 7. Its length is 20, and the resistance R1 is given by 12. plugging this fraction on the calculator, then the value of the area is given by the cross-sectional area. (1.67) times 10 to the power minus 7, because everything is expressed in the SI, so the value of S will be in the SI, which is meter square. But now we need to calculate the diameter. We know that the area S is equal to pi r square. So now dividing both sides by pi, we know that S over pi is equal to r square. So r square is equal to S divided by pi. The value of S is given by this, divided by pi. So r square is equal to over shift pi so it's given by 5.32 times 10 to the power minus 8, but we are interested in the value of r, not r square, so r will be square root of this value. So square root of this answer, and this is equal to 2.31. Let me try it again. Yes, 2.31 times 10 to the power minus 4 meters, because everything is expressed in the SI. And recall that we are interested in the diameter, not the radius. So the diameter is double the radius, which is 2 times 2.31 times 10 to the power minus 4. So this is equal to 4.62 times 10 to the power minus 4 meters. So the diameter of this wire is given by this much. Now if we refer back to the previous figure, so what is the diameter? The diameter is this distance, which is here. And this is the diameter. And in this case, it's given by 4.62 times 10 to the power minus 4 meters, which is equal to 4.62 times 10 to the power minus 2 centimeters, if you convert it to centimeters. Now, and this number is extremely difficult to observe with the naked eye, which means that the wires are very thin. The thing that we have, that we are used to, and the wires that we use them in the lab. Okay, so this is reasonable. Now in number 2, they are telling us calculate the electric energy consumed by R1. Then we are interested in calculating the energy, which is equal to P multiplied by T. The time is given by 5 minutes, but we know that minutes is not a unit of time. In order to convert from minutes to seconds, we need to multiply it by 60. Then 5 multiplied by 60, this is equal to 300 seconds. So E, okay, here they are telling us give your answer in joules and in watt hour. Let's first concentrate on the joules, which is the SI unit. Now we know the value of time, but we need to know the value of power in order to calculate the electric energy. Now power for any electric component is given by U multiplied by I. Now we are calculating the power across the resistor R1 of voltage U1 and resistance I1. So R1 is in parallel with the battery, so it has a voltage of 12, and the current I. So here I1 is the current, okay, current I2 traversing the resistor R1, which is 1 amperes. Now here, okay, it's not a big deal, the naming of the current, it's okay. So 1, which is equal to 12 watts. So P1 is equal to 12 watts. Now energy is equal to P multiplied by T, 12 multiplied by 300. So this is equal to 3600 joules. Now if you want to calculate in watt hour, so this is in joules, now in watt hour. So watt hour means the power must be in watts and the time in hours. So E is equal to P times T. We know that the power is given by 12 in watts. As for the time, which is equal to 2 minutes, and in order to convert from minutes to hours, we need to divide by 60, because for each hour we have 60 minutes. Then going from minutes to hours, we need to divide by 60. So 2 divided by 60. Let me do it like this. Zero point 0.033 hours. So 12 multiplied by 0.033, so this is equal to 0.396 watts hour. So that's it for me in this video, guys. So in the next part, probably I will explain the rheostat and complete solving exercises on this chapter.